All right, hello everyone, this is Mrs. Leopold and I'm going to get you started on Unit 2, Lesson 1. And Unit 2, we're going to be studying it for a long time. As you can see from the front of your booklet, it's quite a long unit and it's all about quadratic functions, which are parabolas. You can see that right here. So we're going to be studying quadratic functions, and before we can do that, we need to graph one and figure out what is a quadratic function, what is a parabola. So the general equation, or the parent function for a quadratic equation, is f of x equals x squared. So remember, f of x is the same as y, so we're going to use this table right here and see what a parabola is going to look like. So we plug negative 3 in for x, so that would be negative 3 squared. Some of you are still making the mistake that when we plug in a negative, remember you must parenthesize that negative and then square it. So it's negative 3 times negative 3, which is 9. So if we went to the left, 1, 2, 3, we went up, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is where the first point would be. Continue that in our table. We're going to plug a negative 2 into the function. So it's negative 2 squared, which is 4. Graph that. Negative 1 squared, which is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So we go to the right 2, up 4. And 3 squared is 9. So I go to the right 3, up 9. So those are the points from the table. So if I connect those points, I would get a parabola. So we call this a quadratic function, and the shape of the curve is called a parabola. Now, what do you notice about the parabola? Well, here are some things that we want you to notice. So does it have a maximum or a minimum? So hopefully you see right here, it does indeed. In this case, it has a minimum. And the maximum or minimum we call the vertex. So this point right here is called the vertex of the parabola. Now, with the vertex of the parabola, there's a vertical line that we can draw through the vertex of the parabola, which in this case, it just happens to be our y-axis. And that vertical line is called the axis of symmetry. And the axis of symmetry splits the parabola into two parts that if you folded it on this line right here, the axis of symmetry, everything on the left-hand side would fold, every point over here on the left-hand side would fold and lie right on top of every point on the right-hand side. So it's reflective, right? It's reflective over the line of symmetry. Now we can write an equation for a line of symmetry. Remember, it's a vertical line in Algebra 1. It's a vertical line going through 0. So when it's a vertical line, you have x equal whatever that value is. So because the vertex is at 0, 0, right, that's my vertex right there, and your axis of symmetry is going to go through whatever the x coordinate is of the vertex. I already answered this question for you. It said, should there be arrows on the ends of your parabola? If so, add them. Well, you can see I already instantly put arrows on there because really these are just a group, or this is just a sample of the domain. We could have any real number and put it in there and get an answer. And so we can put in 5, 5 squared would be 25, and the parabola points keep going onward and onward, so we should have arrows at the ends of our parabola. Now, if we have arrows at the ends of our parabola, then what is the domain? So I can put in any number and square it, and the parabola is going to continue to get higher and higher and higher. So my domain goes from negative infinity to infinity. Or in other words, my domain is all real numbers. Your range, however, is not all real numbers. Do you have any values down here in the negative y values? You do not. So your range has to be all of the possible y values. Well, your lowest y value is 0, so it's inclusive of 0 because that's the lowest it goes. And then those values get higher and higher and higher. So it goes to positive infinity, and remember, we always exclude the infinities. So your range is only from the lowest point, which is the vertex, on up, If we had reflected that parabola over the axis, then of course it would be going down. And we'll have some of those later. Okay, our next question. Is this parabola, the function, a one-to-one function? So hopefully you're shaking your head no, you're already answering that. And why is it not a one-to-one function? Because it fails what? Hopefully you're saying the horizontal line test. So BC is because. So right, if we drew in the horizontal line, it hits it more than once, therefore it fails the horizontal line test and it is not one-to-one. Okay, so the point of this unit is not only studying our parabolas, but most specifically, we are going to study parabolas in vertex form today. And in vertex form, it is the easiest form that allows us to figure out how we are transforming our quadratic functions. And we learned about transformations in Unit 1. Remember when we did y equals, and we had our a, and we had our b, and our x plus h, and our plus k? Well, we're going to apply these three transformations to the parabola today. We are actually not going to worry about horizontal dilations, but we will focus on vertical dilations. We will focus on shifting to the left or to the right, and we will focus on shifting up or down. We will look at also a vertical reflection, right? So, and we'll be talking about r dt. We reflect first, then we dilate, and then we translate. So all of that's going to come back in this unit, specifically in this very first lesson today. So if you understand, hopefully after lots of practice, it's not going to just maybe come immediately, but you're going to have this parent function of the parabola, f of x equals x squared. You're going to kind of know what that looks like right away. You have your vertex, right? And then from your vertex, you go right one, up one, left one, up one, because if you go right one, you go up one squared, right? So I always say right one, left one, or left one, up one. And then you also could go right 2, up 2 squared, which is 4, left 2, up 2 squared, which is 4. So remember, it's symmetric, so they should be lining up. They're reflective of each other, all these points. So right 2, up 4, left 2, up 4. So I usually call it the 1-to-1, 2-to-4 relationship from the vertex. So I'll probably refer to that when I'm in class, 1-to-1, 2-to-4, and that's kind of how you quickly get the idea of what a parabola is going to look like. Okay, so let's apply our transformations here. So really our ultimate goal is for you to look at a graph and be able to write the parabola based on its transformation and its parent function, or if we give you the equation, you can draw the graph. So we can either give you the graph and you can draw the equation, write the equation, or we give you the equation and you can draw the graph. So in these examples here, it's just trying to introduce you to how to write the equation of a parabola if it has been transformed. So it says the function f of x is transformed to create the graph g of x. So you can see the black is the g of x and the red is the f of x. So we're going to take f of x and we're going to transform it to g of x. Describe the transformations below, or that map f of x onto g of x. So we're going to describe it. So first of all, let's look at the vertex, right? This is a 1-to-1, 2-to-4 relationship. The first thing you might notice, remember we're going to go in the order of r, d, t. We look for reflections first, then we look for dilations, and then we look for translations. Sorry, I put those letters too close to each other, so I didn't get to write that out very nicely. Apologies. So the first thing you might notice is there's a reflection, right? It reflects over the x-axis. So that's the first thing that happened. It reflected over the x-axis. Okay, number 2, after it reflected over the x-axis, these points are going to be here. So your graph would look something like this. Okay, then after we reflected, what do we do next? Well, hopefully you're just saying to yourself, we just shifted 1, 2, 3 units to the right. Right? This went 1, 2, 3 units to the right. 1, 2, 3 units to the right. So we translated 3 units to the right. Now, how can I show those transformations using function notation? Right? So your g of x is now going to do what? Well, a vertical reflection. This is a vertical reflection, right? It flipped up to down. So it's a vertical reflection. So that's associated with your letter A. So my letter A has to be negative. Now, it's still a 1-to-1, 2-to-4 relationship, so there was no vertical stretch. So it's just a -1 there, and I don't need to put the negative or the 1, so I'm just going to put the negative in front of the f of x. Then I saw in the green, remember, it shifted 1, 2, 3 units to the right. So if it went 3 units to the right, remember, going to the right, we do the opposite inside. So it's going to be a -3 instead of a +3 because we moved 2 units to the right. And anything associated with horizontal movement is the opposite. Anything inside here is the opposite of what you think it's going to be. And then it didn't shift up or down, so this is it. This is your equation for the function. Now, this is not actually the function itself. It's not f of x. We actually know what f of x equals. It equals x squared. So instead of writing it as f of x minus 3 or negative f of x minus 3, we're actually just going to put in those transformations to x squared. So g of x equals, well, usually we would have our x squared, but instead of x squared, it's going to be x minus 3 squared. And then notice we have this -1 in front of it, where you don't really need the 1, right? So you can just have a negative times x minus 3 squared. So if we're looking at our original function, A is telling us a vertical dilation, or if it's negative, it's also your reflection. Then you're going to have your x minus your h squared plus your k. So your h is going to tell you your hk is your vertex, right? So you do the opposite. If it's minus k, it's going to be a positive h. If it's plus k or minus h, it's going to be, if it's minus h, you're going to have a positive h here, and if it's positive k, you're just going to have a positive k. So hk is your vertex, and then you have your vertical dilation and also the reflection if it's negative in front. So you can see your vertex here was 3, 0, so that's why we have a 3 here. We have a plus 0, so you just don't even need to put, oops, I don't know what happened there. You don't even need to put plus 0. Again, I know it might be a little confusing, but we'll keep going a little bit each time and see how you do. Hopefully you'll catch up. You'll pick it up, or you can just ask me questions. See, so you could even, I have no idea what just happened. All right, so here we are practicing how we can look at a graph of a parabola and write it in function form and write the equation of that parabola. So let me just remind you. We have the letter A, which is related to our vertical dilation as well as the reflection. And then you're going to have x minus whatever the x coordinate is of the vertex, so x minus h, and that quantity squared because it's a parabola, and then plus k. So hk is called the vertex. So if we look here, traditionally, where the parent function has a vertex at 0, and then when you plug in a 1, you would get 1 squared. When you plug in a 2, you would get 2 squared, which is 4. And when you plug in a -1, -1 squared is positive 1, and -2 squared is positive 4. So this is what the original parent function of the parabola looks like. F of x equals x squared. So what happened to that original parent function? Well, the only thing that happened was our vertex went down 1, 2, 3, 4, 5. So our vertex is at 0, -5. There was no dilation, there was no reflection. So the only thing we have to do is write the h, which is 0, and then I write my k. So do I even need that x minus 0 squared? No, I don't. So actually, all I'd have to do is go x squared minus 5. And that would be my answer. Okay, let's look at the second example. We have our original function, which is this yellow one over here. That's my original, f of x equals x squared. What do you notice? The first thing that happens is this is reflected down. So it's reflected down. The vertex is still at 0, 0. So my vertex is still 0, 0, but it was just reflected down. And every time you have a vertical dilation, or sorry, a vertical reflection, your A has a negative in front of it. And then my vertex is at 0, 0, so I don't need to do any h or k because they're both 0, so it's just a negative x squared. Okay, let's try letter C together, and then I want you to pause and try the next 3 on your own. So letter C. If you're looking at this original yellow graph, which now I've just traced over in green, right, and you're comparing, okay, not sure what happened, just had a little technical issue. Anyway, if we were to draw the original parabola here, so we'd have a vertex, we go right 1, up 1, right 2, up 4, 1, 2, 3, 4, left 2, up 4, left 1, up 1. So this is our original parabola. So you can see clearly that the new parabola is opening downward. And so the first thing you might want to say to yourself is, I need to have a reflection downward. So I need a negative A. Now, was there any stretch value here? So you can see no, it's still 1 to 1 and 2 to 4. So it's 1 to 1 and 2 to 4. And so there was no stretch value. So we don't have to worry about an actual value for A. It just stayed as 1. So it's just a negative in front. The next thing I have to do is my vertex. So where is your vertex now? Your vertex is up here at the top. That's at 0, +5. So I put a 0 in here. Okay, is that really necessary? No, it's not. And then I have my +5 on the outside. So in other words, I don't need that. I could have just written f of x equals -x squared plus 5. So I reflected the parabola down across the x-axis, and then I shifted it upward 5 units, and that was it. So this would be my equation for the parabola. So if you feel like you're getting the hang of it, go ahead and pause and try letter D, E. F is a little bit harder, and we'll talk about that in a minute, but go ahead and pause and see how you do on your own. Okay, so for letter D, the vertex right here is just 3, 0. There wasn't any reflection, there wasn't any stretching, and so all we did was move to the right 3. So I put in right 3, which is -3 instead of +3. It didn't go up or down, so it's just x minus 3, the quantity squared. For letter E, we moved to the right 2 and down 1, and so you can see I put in -2 because we moved right 2 and down 1, which is -1, and so this is my new parabola. F of x equals x minus 2, the quantity squared, -1. So now you see why we were learning all that transformation stuff in the first unit, because we're applying all of that right now. Now, letter F is a little trickier, so that's why I paused to do it with you. Maybe you already did it and you're just checking your answer. But usually, remember, we go 1 to 1, 2 to 4. But here, this time when we go to the right 1, I don't go up 1, I go up 1, 2, 3. So in other words, this is my x value, this is my y value. My x movement is right 1, my y value is up 1, except it went up 3 times as much, which means I have an a value of 3 because it tripled what the distance usually is. Usually it's only up, right 1, up 1. See over here, I'm doing it on letter A. So what do I have now? I have to triple the vertical dilation. It went up 3 times stretched higher, so that's a 3 for letter A. But my vertex is still 0, 0. So I don't do anything. I don't want to put x minus 0 squared plus 0. That's all unnecessary. So all I had to do was just put 3 times x squared. And that's it. All right, G is a little bit trickier, so I'll do G with you, and then you can try H and I to see how you're doing. So G is a little tricky. Again, this 1 to 1, 2 to 4 relationship is really important. Typically, we go to the right 1, up 1, to the right 2, up 4, right? So it's 1, 1, 2, 4. Except you can see on the second one, the first one's not so clear because that point is in the middle. So you might think it's right smack in the middle, it's 1/2. You'd be right, but you don't know for sure until you look at the second point. The second point was typically supposed to go up 4 units, but it only went up 2 units. And so in relationship to 2, or 4 has what relationship to this new 2? Well, it halved that distance, and so it was actually had a vertical dilation by half because it halved the distance of the original. So when you're doing your f of x, my a value, this is my a value right here. It's 1/2. It's still opening upward, so there's no reflection. There's just a vertical dilation of 1/2. It's shrinking vertically by half its height. And then the vertex didn't change, so it's just 0, 0. Again, I don't need to write the 0, 0. I don't know why I keep doing that. You can just put 1/2 x squared. So pause now and try the next two on your own. Okay, so letter H and letter I. Did you get for letter H, f of x equals 2 times quantity of x plus 4 squared? Hopefully you did. You saw that it was stretched vertically twice its original. So it's usually by 1 to 1, 2 to 4. But instead of going up 1, it went up 2 times higher. And instead of going up 4, it went up 2 times higher. Therefore, we know A is 2. And then my vertex, right, is negative 4, 0. So my H is negative 4. So it's plus 4 because we moved left 4. Letter I had one extra step in there. First, it had a reflection, so it's opening downward, so you need a negative in front of your A. It had twice, it had that, instead of 1 to 1, it was 1 to 2. Instead of 2 to 4, it was 2 to 8, so it doubled its distance, vertical dilation, so that's why we have the 2 here. And then our vertex was negative 3, 5, so we moved to the left 3, up 5. And remember, when you do move to the left, you go the opposite and put a plus sign in here. And then up 5 is just plus 5. Okay, now we are going to reverse what we were doing. This time we give you the equation, we give you the parabolic function, and you have to graph it. Okay, so how are we going to do that? Well, it's in this form right here. Y equals A. Remember, A is our vertical dilation, but it's also relative to a reflection, a vertical reflection. And then HK is your vertex. It tells you how you're going to move from your origin, right, left, up, or down. So right here, when I'm looking at this function, the first thing I want to do is identify its vertex. Remember, anything inside with the x is always the opposite of what you think it's going to be. So if it's a plus 3, that actually means we're moving left 3. And then our minus 4 here means we're moving down 4. So from the origin, I'm going to go 1, 2, 3, and then 1, 2, 3, 4. So this is my vertex. Okay, from my vertex, I typically would go right 1, up 1, left 1, up 1, right 2, up 4, because 2 squared is 4, so 1, 2, 3, 4, left 2, 1, 2, 3, 4, and this would be my parabola. However, it's not the case because I have a half as my A, so I have a vertical dilation by 1/2. So instead of going to the right 1, up 1, I have to go half that distance. So it's right 1, up 1/2. Instead of going right 2, up 4, I go up half that distance, and half of 4 is 2. So it's usually 1 to 1, 2 to 4, but I'm going to half the vertical distance. This is your horizontal movement, this is your vertical movement, right? So this is your horizontal, this is your vertical. So I go right 1, up 1. Nope, I go right or up 1/2 instead. And then right 2, up 4. Nope, I multiply that by 1/2 because my vertical dilation, so I go up 2 instead. It's symmetric, so here is your parabola. Notice I'm always putting arrows, or this is the first time we've graphed it, but you put arrows on your parabola because it does go on infinitely. And the other thing I would say is just end it right here. Put the arrows on right away. You don't need to continue because you don't even know what the x-intercepts are, so don't cross the x-axis if you don't need to, because you don't know the x-intercepts. Okay, remember the axis of symmetry. So your AOS means axis of symmetry, right? So it's AOS. So your axis of symmetry is what splits the parabola in half. So it's your vertical line, and it's your vertical line associated with the x-coordinate of your vertex. So it's just x equals -3. This is your axis of symmetry right here. It's a vertical line going through -3, and whenever you have a vertical line, you set it as x equals. Your domain is all real numbers, so in other words, from -infinity to infinity, because of the arrows on the ends, it goes on infinitely. Your range, however, is only from wherever your vertex is on up or your vertex on down. Because my parabola is opening upward, I'm going to go from 1, 2, 3, 4, -4 and up. So my range includes -4 because that is where my vertex is, and then it goes to infinity. And finally, your y-intercept. Well, your y-intercept is helpful because it's going to provide one more point for you, and it's really easy to get, right? So why am I circling up here? Well, I don't know why I'm circling. It doesn't really matter. But your y-intercept is when x is 0, then you can find your y-intercept. So I'm going to plug in 0 for x, and I'm going to do a quick calculation, mental calculation. So 0 plus 3 is 3, 3 squared is 9, half of 9 is 4.5, and 4.5 minus 4 is 0.5. So my y-intercept is 0, 0.5. So this would provide one more point to help me draw it even more accurately if I wanted to do that. But you don't need to. All right, for this one, you can go ahead and try it on your own. I would pause, try it on your own, and then compare it with my answer when you're done. Okay, did you get this information over here in the chart? Did you get this information here in the chart? I think I just repeated myself. And does your parabola look like this? If so, then great. If not, I'll try to explain it to you really quickly. So here, -6 means you actually move to the right 6. This negative means we're going to reflect over the x-axis, so it's going to open down, right? So that means it's going to open down when there's a negative in there. So down, negative. If it's positive, it opens up. And then, not only that, you have this stretch value, so you have a vertical dilation by 2. So the 1 to 1, 2 to 4 becomes twice vertically its distance. So it's 1 to 2 and 2 to 8 instead. So I have my vertex. My vertex is 6, 0 because I move right 6 and there's no k, so I'd move up and down 0. So I just moved right 6, which is how I got to here. My axis of symmetry is what splits that parabola in half. It's a vertical line. You have to have an equation. It must be an x equals. If you just put the number 6 on your paper, it's wrong, and you'll get a -1 every time. So it has to be an equation. It's x equals. Your domain is all real numbers. Your range this time is all the numbers down here in the negative, so it's from 0 downward. But remember, you always go from least to greatest, so it's from -infinity to 0, inclusive, because the vertex is at 0. How do you find your y-intercept? You find your y-intercept when x is 0. So we plug 0 in for x and solve for y. Well, 0 minus 6 is negative 6. Negative 6 squared is positive 36. And then negative 2 times 36 is negative 72. So my y-intercept is 0, negative 72. Again, remember your vertical dilation and the reflection. Maybe go to the left 1 down 2 or right 1 down 2, twice that distance, and then left 2 down 4, but it's twice the distance, which is 8. Right 2 down 4, or twice the distance, which is 8. All right, example 5, you should be able to try on your own. It's similar to what we've already done. It's opening downward, so you have your reflection. So I would pause. You can see it's opening downward, so it's going to have your vertical reflection. You can see it's not going 1 to 1, 2 to 4. It's doing something different, so you're going to have some kind of vertical dilation. So go ahead and try it and pause and have a look and see if you got the correct answer. Okay, did you get negative f of x equals negative 1/4 times x minus 2 the quantity squared plus 8? Hopefully you did. You have your vertex here. Your vertex is at 2, 8, so that's right 2 and up 8. But this letter A was the tricky one to find out. So you could have said, okay, we usually have a 1 to 1, 2 to 4 relationship, except it was opening downward, which is why I have my negative. And then I went right 2 down 1, so I only went down 1 unit when I went right 2. And so what did I have to do to the 4 to make it become 1? Well, I had to multiply it by 1/4. It went 1/4 of its distance. If you didn't know that, you could take one of these 2 points on the parabola that we gave you, so you could see that it was 6, 4. So the point on the parabola is 6, 4. I put 4 in for my y value, and I put 6 in for my x value, and then I just solved to find a that way. So that's your other option. If this 1 to 1, 2 to 4 isn't really resonating with you, you can actually calculate it algebraically by plugging in one of these points on the parabola. Again, come see me and ask questions if you're not sure. Come during a free or see me personally so you can ask, because I know it gets a little tricky. All right, solving quadratics using square roots. So we're going to solve for x. And if we solve for x, we might call them solutions, but really those solutions are x-intercepts. We might call them roots. We might call those zeros. But x-intercepts are places where the graph crosses the x-axis. Right? So places where the graph crosses the x-axis. That's what roots are, that's what zeros are, that's what intercepts are. Well, x-intercepts, excuse me. So how do you find x-intercepts? Well, x-intercepts occur when y is equal to 0. So when y equals 0, then you can find the x-intercept. So we're going to do that. We have a quadratic right here. We want to solve for x. Solve for x means find the x-intercepts. Sorry, it doesn't say solve for x. It says solve for the x-intercepts. So we want to find the x-intercepts, which means you need to put 0 in for y. So step number 1, substitute in 0 for y. And here we have it. Now, when you have your quadratic written in vertex form, then what is the easiest way? I always want to be the most efficient I possibly can. So what's the easiest thing I can do in order to solve for x? Well, I'm going to try to isolate the part that's squared. Right? So I'm going to isolate that, which means I need to move my minus 4 to the other side. So how do I move that minus 4 to the other side? I add 4. So I get 4 equals x minus 5, the quantity squared. If you have a perfect square, what can you do to that perfect square just to get rid of the square? Well, square root of a square undoes the squaring, right? If you have 5 squared, that's 25. How do I go back to the number 5? I take the square root of 25 to get 5, right? So the square root of 5 squared is just 5. So the square root of x minus 5, the quantity squared, is just x minus 5. but we have two, because we want x squared here, we have to have two possible answers. So that's plus or minus 2. Right, the quadratic, you're going to have two x-intercepts unless the vertex is actually on the axis. So we have two x-intercepts. So how do we find those? We put our plus or minus 2 there. So now we add 5 to both sides. So we get x equals 2 plus 5, which is 7, or x equals negative 2 plus 5, which is 3, right? I have my positive 2 plus 5, or I have my negative 2 plus 5. So my two x-intercepts are 7, 0, and 3, 0. Okay, here are two more you can try on your own. I would pause, try them on your own, plug in 0, right? We're trying to find the x-intercepts. So plug in 0 for y and solve for x. So go ahead and try it on your own. Okay, so I plug in my 0, I subtract 10, I get 2x squared equals negative 10, I divide by 2, I get x squared equals negative 5. Great, I take the square root of both sides. The square root of x squared is x. Oh, wait a minute here. Can I take the square root of a negative number? No. So this is not possible. It doesn't have any real roots. Or actually what we'll say is there are no x-intercepts. So this means that it does not cross the x-axis. There are no x-intercepts. Okay, the last one, if you plugged in your 0, then you should have, the first thing you did was add your 4 to both sides. So you got 4 equals 1/2 times x plus 3 squared. Then you still needed to isolate by multiplying by 2, right? If I multiply by 2, then my 1/2 cancels. So 2 times 4 is 8. And then what do I do to both sides? I take the square root. So I get root 8 equals x plus 3. But remember, you always have to put the plus or minus sign in front. So when you take the square root of both sides, you have a plus or minus root 8. And the last thing I have to do is isolate my x by moving the 3 to the other side. So I would get negative 3 plus or minus the square root of 8. And if you have studied the quadratic formula, then that might look a little bit familiar, but this is a shorter way of solving these problems rather than using the quadratic formula. Okay, the last thing we're going to do is an application problem to try to put it all together so you can kind of see what all these aspects of a graph or how it might relate to a problem or what their role is, and understanding the scenario that's actually happening. So it says a manufacturer of tricycles finds that the weekly revenue, so how much money you're making, from tricycle sales is a function of the price of the tricycle P. A model for the weekly revenue is in dollars and can be modeled by the following equation. So X is our P, so that means this x-axis is the price, and the price is in dollars. And then our y-axis is R of P. And R of P is our revenue. It's how much money that we're bringing in. Okay, so price is, or P is the price per tricycle, and our Y value is R of P, which is the revenue with respect to the price. So how much money we're bringing in. Okay, so sketch a graph of the revenue versus tricycle price. Well, if we have this R of P equals negative 2 P minus 50 squared plus 5,000. Hopefully you're saying, okay, this is like my quadratic equation where HK is the vertex, right? It's just a quadratic equation in vertex form. So my vertex is 55,000, right? I take the opposite of this, negative 50, so it goes to the right 50. So I'm just going to pluck a 50 there. And then it goes up 5,000, so I'm going to put a 5,000 there. So that's the highest it possibly goes. How do I know that's the highest? Because I have a negative in front. So that means the parabola is going to open downward. Now, where do I go from there? Well, usually we go right one, down one, left one, down one. But because of this 2 in front, we're going to go right 1, down 2. But even that's not really going to help us that much. So I need to find probably my zeros or my x-intercepts to help. So in order to find my x-intercepts, I plug in 0 for y and solve for x. So I need to plug in 0 for my y value. Well, your y value is r of p. So I get negative 2 times, I plug in p, or just keep it as p minus 50 squared plus 5,000. I subtract my 5,000 because I'm trying to isolate p. So I get negative 5,000 equals negative 2 times p minus 50 squared. So then I divide by negative 2. So that leads me to 2,500 equals p minus 50 squared. Then I can take the square root of both sides. And when I take the square root of both sides, sorry, I'm going to continue down here. The square root of 2,500 is 50 because the square root of 25 is 5. And we just have our zeros. So remember, you have to put the plus or minus in front of that. And then we get p minus 50. So I either have 50 equals p minus 50, or I have negative 50 equals p minus 50. So when I solve for p, I either get 100 or I get 0. So I have a y, or x-intercept at 0, and I have an x-intercept at 100, and I have my vertex here at 55,000. So my parabola looks something like this. Now I put an arrow over here, and then notice I didn't put an arrow on the right hand side. Why should there be arrows or not? And does it make sense? Well, let's answer those questions. We'll kind of tackle those questions as we get to them in this in the questions below. So it says, what is the maximum revenue from the tricycle sales? So your maximum revenue, this is your maximum right here. And revenue is associated with your y value. So what was the maximum revenue? It was $5,000. You need the dollar sign because we're talking about money. And maximum is a y value. And then it says, what price should the tricycle be in order to maximize revenue? Well, you can see right here, the price is $50 per tricycle, and that's going to give us our maximum revenue. Determining the x-intercepts, well, I already did that. I did that up here, and those x-intercepts were 0 and 100. Now, what do they mean in the context of the problem? What does that mean? Well, hopefully you're saying to yourself, if you sell 0 tricycles, you will make $0. And if you sell 100, or sorry, if you sell 0 tricycles or tricycles at $0, sorry, you just give them away. Excuse me, if you sell tricycles for $0, you just give them away for free, then you're obviously not going to make any money. If you sell tricycles for $100, then you're also not going to make any money because no one's going to buy them, is basically what they're saying. It's too expensive. Then we continue on with that question here. So we had our graph. Yours is on your paper, but I couldn't fit it all on one page. So I have my 50, this is 5,000, this is 0, this is 100. So what is the practical domain for this question? Well, your domain is right here. So my practical domain, remember I said, I had put arrows on my graph? Well, that really wasn't practical. Are you going to sell negative bicycles? Or are you going to have a -1? Even though that parabola would go forever. Are you going to sell negative bicycles? No. Are you going to sell bicycles for more money and then lose? Like, this is negative, right? These are negative Y values. Do you want to have negative revenue? No. So that's not practical either. So your domain only makes sense between 0 and 100. Your practical range, again, your range is going to go infinitely down forever, but that is not practical because you don't want negative money. So your practical domain is either you're going to make $0 or you're going to make a maximum of $5,000. So that's your practical range. Notice your domain is exclusive, right? You don't want to make $0. So yeah, we should change this. Apologies. This should be an exclusive here as well, because you don't want to make $0. You want to make money. You want to put money in your pocket. So I would say your practical range is 0 exclusive up to 5,000 inclusive, because you do want to maximize your revenue. And finally, it says, what should the price per tricycle be for the revenue to be at least? Okay, what does the word at least mean? It means that's the minimum it could be. So it's greater than or equal to $1,800. So you could go across here, put in $1,800 and see where that intersects the graph. And so what is this 1,800 representing? What is the 1,800 representing? It's representing the Y value. And so I'm going to say, when is 1,800 going to equal -2 times P minus 50 squared plus 5,000? So I subtract my 5,000, right? And I get 3,200 equals -2 times P minus 50 squared. I divide by -2. And sorry, this should be -3,200 because 5,000 is bigger. And I get 1,600 equals P minus 50 squared. And then I take the square root. I shouldn't need a calculator for any of this. I'm going to continue over here. I get plus or minus 40 equals P minus 50. Then I move the 50 over by adding 50. So I get 50 plus or minus 40 equals P. So 50 plus 40, which is 90, or 50 minus 40, which is 10. So what should the price per tricycle be for the revenue to be at least? So that means a minimum of $1,800. Well, the price should be $90 or it should be $10. Now, that's to get exactly 1,800. So it's technically not my answer because the question says at least. So we want this interval that goes from between those two prices. So it would be from 10 to 90 inclusive, because that is when it includes the 1,800. So it's $10 to $90. Phew, that's a long lesson. This unit is going to have a lot of information. Ask me questions, ask me questions, ask me questions. If you're not sure, go back and listen to different parts of this video if that helps. I'm here to help you and answer your questions, so just let me know what I can do to support you. Bye. It's representing your Y value.